problem 4, and this one is about a plane flying in wind. So a plane is capable of flying at a speed of 180 kilometers per hour in still air. The pilot takes off from an airfield and heads due north, so he's going pretty much, yeah, just straight like that, straight up north, according to the plane's compass. After 30 minutes of flight time, yeah, the pilot notices that due to the wind, the plane has actually traveled 80 kilometers at an angle 5 degrees east of north. So it actually flies over here, kilometers. So 5 degrees from that over there. So we're asked a two-part question. So part A, what is the wind velocity? And B, in what direction should the pilot have headed to reach the intended destination? Alright, so let's take a look at the first part. So solution to A, so we consider velocity vectors for the plane and the wind. So we want to find out what the wind velocity is. So let's write these in vectors, and let VI vector be the initial or intended velocity for the plane, and let VG or subscript G vector be the actual velocity relative to the ground. Because again, you have the plane like this, and it's flying, and so you're flying straight. But then even if you're pointing north there, you could be being pushed across by the wind. So you could be over here, a really bad plane, like that. So anyways, you could be drifting across, even though you're still pointing the nose forward. And also, if W is the velocity of the wind, Vg is the resultant. Vg is the resultant, and that's actually the actual velocity. That is the vector sum Vi plus W as shown in the figure. So let's say you're flying across here. So put a dashed line like this, or let's put a flat line so we get the angles. So it's flying straight due north. This is the intended Vi. So we want to go Vi here. But what we end up actually flying towards is we fly 5 degrees. We'll put a 5 degrees like this. And yeah, we end up flying over here at an actual ground velocity, or the resultant here. And we're going to have a wind direction. I'm going to put a W like this. So that this is a vector sum there. So we have Vg like this is equal to just basic vectors, Vi vector plus W vector. And also, if this is 5 degrees and you're going due north initially, the intended scenario, so then this angle is going to be 90 minus 5. So this is a right angle like that. This is going to be 85 degrees. Alright, so continuing further, so we know that Vi, we know that this vector, this is the intended velocity, and that's just going to be 180j, and this is due north again in our ijk components. Like that. That's basically going in the y direction, or the north direction there. So again, it was 180 kilometers per hour is the intended velocity we were going at. Yeah, so that is there, and then let's write this out. And since the plane flew 80 kilometers in a half hour, the absolute value of this ground velocity is going to be equal to 160 kilometers per hour. Because again, that's 80 in half hour, so times it by 2, 160. So it actually got slowed down, so some of the wind is hitting it directly at its face. So it's actually going down as well. So then you can see that here, after 30 minutes of flight time, the pilot notices the plane has traveled 80 kilometers at an angle 5 degrees east of north. Yeah, so thus we have, and what I'm going to also do here is, first of all, we're going to determine this Vg as a vector. So and to do that, well, we could notice this part right here. So we could take that, so it's going like this. This is Vg. This is Vg like that, and yeah, I'll just put a Vg like that. And we also know that this right here is 85 degrees. And again, using basic trigonometry. And then this height right here, so I'll erase this, goes like this. Yeah, this right here I'm just going to put like that. And using trigonometry, this right here is the tangent, the sine of this one. I've included this one here. So this is going to be the absolute value of Vg like this, with this is the full distance right here. Absolute value of Vg like that, and that's going to be this is going to be sine theta. As again, remember, sine theta is equal to opposite over opposite over hypotenuse. And then so the bottom right here is just going to be g, the absolute value sine, times by cosine. So the adjacent over hypotenuse. And then just move over the hypotenuse to get the adjacent. Yeah, so basically writing these in components. So this VG. So VG as a vector is going to be, the VG velocity, ground velocity or resultant, etc. is going to equal to, we just add the component. So the horizontal component in the I direction is going to be VG cosine theta I plus, and then the vertical or the north direction is going to be, this is going to be an absolute value sign right here. So the absolute value sign, again, velocity has direction, magnitude doesn't, right there. The speed doesn't. Like this. This is going to be sine theta j. And we know the absolute value of the ground velocity. That's just going to be the speed, so 160 kilometers. So 80 times 2. Yeah, so this is going to be the I component is going to be 160 cosine theta is 85. And then this is going to be our I plus 160 like that, and then sine 85 degrees, and this is our j component. And now plug this into the calculator, we're going to get roughly equals to 13.9 I and plus 159.4 j. And yeah, we can just box this whole thing in. Alright, so that's what we have there. Now we can do a quick calculation check. So my OneNote has a built-in calculator, so you can just go erase this, just put cosine, yeah, so 160 times cosine 85, and it's automatically in degrees, and it goes 13.94549, etc. And then similarly for this one, 160 times sine 85 degrees, 159.39, rounded up so 159.4. So now we could solve for the wind velocity because we have both we know VG and we know VI, so we should solve for W. So basically we'll have VG is equal to VI plus W, like that, plus W like this. Yeah, so in other words, we're going to have W, let's put an arrow here, plus W is equal to, this is going to move this over to the other side, so we're going to get a VG minus VI. So we have to subtract vectors, and we can do this, yeah, but let's just write the components out. We could write them in IJ or just write them as a vector bracket form. Well, I'll write this one right here. So VG is equal to 13.9 and 159.4. 13.9 and 159.4, and then subtract this by VI. And VI we know is just going due north, so the horizontal component is 0, and then the other one is 180, is the vertical. Alright, so if we subtract these, what we end up having is 13.9 minus 0 is just 13.9. So this is going to be 13.9. And then likewise here, 159.4 minus 80, 180. Yeah, so here we need to do some subtraction since this 159.4 is on the other side is minusing. This one is bigger. What we could do is do it manually. You put 180 on top and then subtract this by and put a negative all over the whole thing. So put a negative like this, like that. So we're just going to do this all by hand manually just for fun sake. 180 minus this 159, so the difference, 0.4, 0.0. But then we're going to get a positive number, so we need to add a negative to it. Like this. So we're going to get a positive. So I will bracket this and put a negative. Alright, here, just fix that up, and now we'll just solve it. So this one here, this is 0 minus 4. We need to basically add a 1 here. So we need to subtract one of these, but because it's there's already a 0, this is going to be a 9, and this crosses out to a 7, so we take 1 away. This becomes a 10 right here. So this is going to become a 10, like that. So we have 10 minus 4 is 6, and then 9 minus 9 is 0, and then 7 minus 5 is 2. And this goes 1 minus 1 is 0. So we have 20.6, and we have to put a negative because we flipped over the bigger number on the top. So this is going to be equal to negative 13.9 and negative 20.6, or you could write this in IJK format. This equals to 13. Yeah, let's put this again. Yeah, so 13.9I minus 20.6J. And this is the wind velocity. And likewise, the absolute value of it, or the wind speed, is going to equal to, this is again relative to the ground, just whatever it is. Yeah, so the actual speed of it. This is just the velocity includes direction. So we just take the basically take the square root of it. I mean, we just use the basic magnitude formula, and that's just the Pythagorean theorem. Basically, we just sum these up and square them. So square and sum it up. So we're going to get 13.9 squared plus 20.6 squared, like that. And plug this into the calculator, we get roughly, this will equal to 24.9 kilometers per hour. And that is our wind speed. Alright, so continuing further, just do a quick calculation check right here. So square root 13.9 squared plus, and then negative 20.6 squared. And yeah, this is a negative, it doesn't change anything. There's a negative like that. It's still going to be, squared there. It's still going to be positive. So we'll put that in like here. This equals to 24.85, and then round it up to 9 there. And also here, just to double check my manual subtraction there, you just put this here, 159.4 minus 180. This equals to 20.6. Alright, yeah, so now we have it all correct. So now we can move on to the solution to part B. So let's go and read that again. So part B says, in what direction should the pilot have headed to reach the intended destination? Alright, so let's draw this out. So basically we have to fly to the west, and then it will hopefully go to the north. So let V be the velocity the pilot should have taken, and the pilot would need to head a little west of north to compensate for the wind. So let theta be the angle V makes with the north direction. Alright, so let's graph this out. So let's say we have our ground speed, it ends up going over here, VG. I'll write this as VG like this. And this is our, due north is where we want to go. So then this is going to be right angle like this, and now we're going to fly a bit to the west. So this is our V, like that. So that's our V, and this is at an angle theta west of north to compensate. And now we have our wind. It's going to be pushing this way, the same direction, W, like that. So wind is always the same as the previous one. And now what we're going to have is we'll have another right angle right here. And so I will extend this out. Yeah, I'll extend this out further, so what we end up having is a right angle like this. And this one is going to be this angle right here. Well, instead of looking at that, we could just use the full 90, just the full thing right here. So 90 degrees plus theta, and then and I'll show you why it's the same thing. And what we end up having is this side length right here is going to be, this is going to be the magnitude of the velocity we want to go, so the speed times by sine theta, similar, just using basic trigonometry. This is sine theta plus 90. Yeah, and let's put, this is actually 90 plus, 90 degrees plus theta. And yeah, so we have this right here, but notice we could also use, you could also use cosine here. Cosine, instead of we can use the cosine of the theta angle and use it over on this height. But the thing is, with this case, we have to always keep in mind where is negative and where is positive. I'm just going to keep it like this because the solutions manual has it like that. Because if you go on the left side right here, this one will be sine. We're going to be positive number, but it's going to the west. And then in this coordinate system, we have west is a negative. Because we have this angle going from this side here, where 0 is on the positive axis, on the positive x-axis there. So anyways, the next part here is this is the absolute value of the speed, and then cosine 0 plus 90 degrees, like that. That's the cosine of it. And again, just a note, this right here would be, this is going from backwards over there. This is the same as writing 90 minus theta. or we could use it over there. Again, depends how you want to look at it. But if you just recall the trigonomic, for example, cosine, and same thing for sine. So I'll just put cosine right here. Cosine theta. So cosine theta looks like this and goes up like that. This is at pi or 90 degrees. That's at 90, and this is at 180 or 270. And 180 is right here. So so basically, if we have, and it's symmetric. So let's say we had an angle across here. This is between here and here is theta. So if we go 90 minus it, we're going to have a positive number, but we want an actual negative there, so we'll have to put a negative if we use this one here. And then, but then if we go across to the other side, so right here, this is, I'll put it like this. This right here, theta. So basically, basically 90 plus theta will have a negative number, which is what we want. So it's exactly the same thing. This is going to be plus, this is going to be negative, and exactly the same thing. It's just symmetric. But all right, so now that we just established that, I just wanted to do a quick sidetrack on trigonometry to understand. You could just use the full angle wherever the line is. If you go all the way around, you can just add. Just ignore how the triangle looks like. It's going to end up being the same thing, but the signs always are kept under track. So basically, continue further. So with effect of the wind, the actual velocity with respect to the ground will be v plus vw. So vg is there, which we want to be due north. So what we'll do is vg is equal to, and again add the vectors, v plus w is equals to v plus w. This equals 2, and let's just all write it out in component format like this, or vector bracket format. So v here is going to be, this is going to be the absolute value of v. This is 180. I'll just write it all down quickly. So 180, and then sine like this, and we need to find out that angle. So it's going to be sine theta plus 90 degrees, and then the next one's going to be, actually no, this is the other way around. This is a cosine. This is the horizontal one. This is the I component, and then the next one is the 180, like this. 180, and then this is sine theta plus 90, like that. And then we have to add the wind, plus the wind is going to be, and we already know the wind is this here, 13.9 and negative 20.6. But instead, let's just use the full values. And the full values here, this was the VG, and then we just subtracted by 180 on this other side there. So instead of actually solving it all out, I'll just use the exact numbers. So this would be 80 cosine 85. So this is so the first part right here. This is 13.9. Is 160 cosine 85. So I'll just go plus 160 cosine 85 degrees. And again, just because the solutions manual did that, that's easier to work with. I guess it's just more accurate instead of having to always use the approximation format. Then the next one is going to be 160, and then this is going to be 160 sine, so 159.4, and then subtracted by 180. So sine, so 160 sine 85 degrees minus 180. So just put it all together like that. All right, and now we want this to be 0. So the horizontal component, we want it to be 0. So we want it to equal to 0. And then on the other part, we just add those up. So we'll just have 180 sine. Yeah, because that's the thing. We want it to be due north. So now we just have to find what angle it is to make it 0 there. And this can be sine theta plus 90. Like this. And then this is going to be, now we just add this part here, plus 160. Sine 85 degrees minus 180. So that is our velocity. And so we want this part right here as 0. So to do that, we need to equate, or just sum those all up to 0. So in other words, we want so 180 cosine theta plus 90 degrees plus 160 cosine 85. When you add the horizontal components, we want it to equal to 0. So we want that, so now we just got to solve it. And to do that, let's move things around so that we're going to have a cosine theta plus 90 degrees equals 2. Move this over to the other side. So negative, and also divide this out. So we're going to get a negative 160 divided by 180, and then a cosine 85 degrees. All right, now if you plug this into the calculator, you're going to get, this part's going to be equal to roughly negative 0.0775. And so this means now we got to solve for theta, and we just take the arc cosine of it. So theta is going to be roughly equals to, because we're using approximate form right there, 0.007. So it's going to be roughly equal to the inverse of cosine negative 1. Power negative 1, just an inverse cosine or a cosine or arc cosine. Now it's going to be, this is going to be negative 0.0775, and then minus, move this over to the other side after we get that out, so minus 90. And now this roughly equals 2. Yeah, this is going to equal 2. This is going to be, it's going to be equal to 4.4 degrees, and I'll show you the calculation too. And this is going to be due west. So I'll put this like this, like that. Yeah, so basically, thus the pilot should have headed about 4.4 degrees west of north. And here's a quick calculation check. So negative 160 divided by 180 cosine 85. Plug in the calculator, OneNote built in, and automatically solves that. So negative 0.00747, rounded up to 5 there. And then also a cosine, you could just solve this for the angle, equals 2. And I put the exact one here. I just put this whole thing inside here instead of using this rounded up one. So negative cosine 60 divided by 180 cosine 85, all that minus 90. You can do that, all that, and it solves it automatically over here. And also, lastly, I added this one right here because we didn't need this part. We weren't asked, but we can use this to solve the ground velocity. And basically, it's heading due north, so all we need is the j component. So 180 sine theta plus 90 plus 160 sine 85 minus 180. So plug that all inside, and I just use this 4.44, just easier. I just round it up. So 180 sine 4.4 plus 90, and then plus 160 times sine 85 minus 180. Plug this into the calculator. We get 158.86. So I rounded up. So the final ground speed is about, say approximate, it's not roughly, it's pretty accurate. So it's approximately 158.9 kilometers per hour, which is a bit slower than the previous 160 kilometers per hour. That was the ground speed that we were initially going if we had due north. Because this time we were headed more head on against the wind, because the wind's going this way, and now we're going to be, initially we were going this way, now we're going flying over 4.4 degrees more head on, so we're going to slightly go slower. So the final speed is actually going to be a bit slower. It's going to go down a bit. So it's not the 160 kilometers per hour. Now it's 158.9. So it's a tiny bit slower. Yes, epic stuff.